of you got your minds blown by James with that talk about lenses. Yeah, so I'm going to do the same. I'm going to blow your minds as well because I'm going to talk about type systems. And by the end of my talk, I hope that you will learn why they're useful and how they can help you write better code. So I'm really excited about this talk, and I spent way too many hours down the rabbit hole researching type theory, but I've distilled it down, and I hope that I can share some pro tips with you today to help you write better programs. It's a very deep topic, and I've learned a lot about type systems as well as functional programming, and I hope you will too. Functional programming is notoriously unfriendly to beginners, so I hope this talk will change your mind. But before we begin, a small warning. There is code and math in this talk, so I'm sorry. But I will try to do my best to avoid jargon. When I do have to use it, I will explain it. So another quick show of hands, how many of you have shipped a bug into production? Everyone, yes. So I know we have, right? We are all human. Programming is hard, and it's really easy to add bugs into software, especially in the wild west that is JavaScript. And when bugs inevitably happen, you feel pretty terrible about it. And I don't know about you, but I occasionally get these real crises of confidence, especially if you can't figure out what the cause of the bug is. But then you do find out what the bug is, and then all is good in the world, and your confidence is restored. I've been programming for a while now, so I've seen my fair share of JavaScript errors, as I'm sure you have too. So here we have everyone's favorite undefined is not a function. Swipe left. And I don't know about you, but these kind of type errors are just not my type. I want to swipe left, turn everything off, drink hot chocolate when I see one. On the other hand, I've grown to really love working with types on top of JavaScript. And I primarily use TypeScript for my personal projects, as well as at work, and I'm in love. Flow is also a really attractive option. It has a number of differences compared to TypeScript, but you can also use it to statically type your code. But in this talk, I will be using TypeScript examples. I also wanted to briefly talk about GraphQL, if we have time, which is a really interesting way to deliver a type system over the network. So my name is Lauren. I'm an engineering manager at Netflix, and I ship bugs into production. Confusingly, I have many internet handles. On Twitter, I am SugarPirate with an underscore. And on GitHub, I'm Potato, but with an E. So clearly, I'm not very good at the internet. So don't steal my usernames if there's a new website coming up. But what is a type system other than something that yells at you a lot? There are many different definitions, but my explanation is a type system is a way to add constraints to your code. And the type system is there to help you enforce logic that is consistent within those constraints. But why? Why are constraints useful in your code? So here's my bold claim. Constraints are really great because they limit the number of bugs that can happen in your program. So let's look at some examples. Here we have a very simple function. It takes one argument and divides it by 2. How many ways can this function fail? I came up with some possible inputs that I could pass into this function. We have our usual suspects like null, undefined, numbers, strings, and so on. Now I want to enumerate over all of those inputs, and after running this, we should see an array of test results. So let's run it in our console and see what happens. Unfortunately for us, null and undefined don't have methods on them. But wouldn't it be nice if the compiler could tell us, like, I don't want to have to wait to run the code in the browser to find these kind of bugs manually, or even to have to write a million unit tests because I'm really lazy. And this is just a simple function, like dividing it by 2. So in JavaScript, your first instinct might be to add checks for null or undefined, or even to define undefined as a function. But you end up having very defensive code, and you're checking argument types in your functions, and these are only checked at runtime, so you're actually shipping more code to the browser. Which is fine, I guess, but I know it can be really frustrating not being able to catch these kind of bugs before you ship into production. So anyway, if we fix the error and we run our program again, we'll see that most of these inputs throw type errors or result in some kind of nonsensical value like not a number. So let me ask you again, how many ways can that function fail? Think about all the possible inputs that you could pass into that function, every single one of them. There is an infinite number. Sorry. There is an infinite number of permutations of garbage you could pass into this function. You could give it an array of 11 ones, an array of 1,000,000 8s, or 100,000 character string. They would all cause problems. So now using TypeScript, let's add the simplest possible type annotation to drastically constrain this function down to only accepting one set of types. So now x can only be a number, and the compiler will yell at me if I pass in anything else. Now, if you try running this function with every single number possible in JavaScript, you'll find that none of them should cause an error, at least at compile time. So in most cases, this function is what we call total. So my bold claim is that types and constraints will reduce the bugs in your programs. So today we're going to look at a very brief introduction into TypeScript, some background into type systems, and how it can help you write better programs, and also explore what it means to have a type system over the network. We've briefly seen what types in TypeScript look like. But let's learn some basics to establish a foundation for the next topic. I'm not going to go through everything, so don't worry too much about the syntax. I want you to focus on the ideas, and you can always look up the syntax later. So first, let's look at some simple examples. We have variables, which I hope you use all the time. You specify the type after the variable name. And these two declarations are actually both equivalent, since TypeScript can infer the type, even if it's not explicitly declared. For lists, you have to tell TypeScript as well what kind of array it is. So here, number square brackets means that it's an array of numbers. You can also define your own types. Here, I've made my own type that's called server stacks, and it's a union of string literals, meaning that anything that has this type can only be one of these exact strings. You can also define interfaces. Here I have a user interface, which describes the shape of an object. But interfaces can also describe functions. So here we have a function that takes an argument of type user. And it knows that isAdmin is a Boolean type on the interface that I defined earlier. So obviously, you would not be able to assign that value, a property to 1, which is a number. And this is all caught for you at compile time. And if you use like an editor like VS Code, you also get a nice red squiggly line and an error message while you're programming. So those are just really basic examples. And again, don't worry about the exact syntax. Remember the ideas. Everything has a type. It could be a primitive type, like a number or a string. It could be a function. It could be a user-defined type or interface. But these all describe the kinds of things that make up your application. So now I want to talk about how you can make your types reusable, just like how you make your code reusable. MakeArray is a simple function. It takes a value x and then puts that inside of an array. But what I've defined here only covers the numbers, strings, and booleans. But what about objects? What about my own types? What about symbols? What about class instances, and so on? How can you type this function so that it can accept any type without defining all of the possible functions, but still give you the type safety that you come to expect? So the answer is to make it a reusable generic function, which you might have seen something similar in James' talk with the interface for lenses. So notice that the function logic itself hasn't changed. Only the type signature has. But I'm going to tell you how to read this. So the first thing I want you to notice is the single letter T in pointy brackets. So this is a type variable. And much like a regular variable, it's meant for types. And this tells TypeScript that this function is generic and can work over more than one type. If you want to go back to your colleagues and get fancy, you can say that this is called parametric polymorphism, but most people say generic. In our function arguments, we can then say that x is of type t. And this will capture the type of whatever was passed into the function and says, let t be the type of the argument x. So this could be a string, this could be a number, a user, whatever you pass into it. And then later, you can use this t variable in your type signature. So finally, we specify the return type of this function, which in this case returns an array filled with items of type t. So now when you're using your function in your editor, you'll see that TypeScript will know how to guide you. If I pass in a number, when you hover over this function, it will tell you that it returns an array of numbers. And if you pass in a string, it knows that it returns an array of strings. So this is just a very simple example, but it's also very powerful because it helps you reuse your types and helps you not have to repeat yourselves. Here's another example to drive things home. This map function is also generic and takes two type arguments, a and b, which we will use later. Map takes two arguments. The first is a function and then a list of items. The first argument is a function and takes a single argument of type A and returns a single value of type B. And the second argument is an array of items that are of type A. And then the return value of this function is an array of items that are type B. So just looking at the type signature alone, can anyone guess what this function does? And as you might have guessed, I hope you guessed it, the function is kind of like array.map, where you can map over an array and transform the values of that are contained within the array. And with this type signature, TypeScript knows how to type your function accordingly based on what you pass into it. And you will know what is returned without you having to actually evaluate this function. And now you can really think about how your functions compose because you know what goes in and what goes out. So we looked at some high-level concepts, and again, don't worry about the exact syntax. Focus on the ideas. And if you recall earlier, we talked about how many ways that first program could fail. Having types mean that your functions and classes can specify constraints about what can be passed into them. There is a lot that functional programming can teach us, and if you're interested in learning more after this talk, check out the videos that I linked to at the bottom of this slide. So type systems are really grounded in mathematics, and so is functional programming. And interestingly, type systems can also be applied to object-oriented languages. The concepts behind this are pretty interesting, and I think it can help us understand why type systems help us write better code. But I do have to say that a lot of functional programming jargon and terminology can be very off-putting. Like this is completely like a troll tweet. It's not actually real concepts, but it kind of looks like it. I hope that doesn't scare you. So let's start with a quick high-level overview. As I said, functional programming is a practical implementation of mathematical theories. We have proof theory, which is about constructive logic and mathematical proofs. And then we have category theory, which is about algebra, how things compose. And if you've heard of abstractions such as, monoids, functors, monads, lenses, these are all examples of categories within category theory. And then you have type theory, which is about programs and the idea that propositions are types. So Curry, Howard, and Lambeck are logicians and mathematicians who independently found that these three seemingly different mathematical theories were describing the same idea in different ways. And so the Curry, Howard, Lambeck correspondence is really the relationship between these three theories: proof theory, category theory, and type theory. So if this sounds arcane to you, don't worry, I'm going to try my best to explain. So the key takeaway I want you to have is that propositions are types. For example, my type signature states that given two numbers, x and y, a number exists. And programs are proofs because, they're proofs of those propositions. Because you don't just get to say that things are true, you have to prove it. You have to show your work, like in math homework. So x plus y is a proof that a number exists. We're going to revisit this again later and to see why that's useful. But let's take a look at functions again, not in the programming sense, but from a mathematical perspective. So this is a function as described in mathematics. In plain English, this function maps an object of type A to an object of type B. And pure functions, if you know what they are mappings. for a given input, you'll get an output in return, and you always get the same output for a given input. And note that object here doesn't refer to JavaScript objects, but just ordinary objects unrelated to programming. Now remember what I said earlier. Types are propositions. They assert that something is true, that something exists. This function will return a number is an example of a proposition. And our programs, or the actual implementations that we write for these type signatures, are proofs. A number exists because here in my code, I have produced the number 1. So what I'm trying to say is that type checking is really proof checking. And if you work backwards from that, what this means is that if you write good, solid type signatures, you can really let the type system suggest the implementation for you, like we saw in the map example earlier. And this is, you can kind of think of this like type-driven development. So in theory, you could even declare all of your types up front and your function type signatures without writing any actual code. And if it compiles, your program should just work. Then it's really a matter of you filling in the details, proving that those propositions that you defined are true. So let's start with a concrete example. This function takes a list of items and returns the first one. Once you've written this type signature, the implementation sometimes seems pretty obvious. So for example, if you try returning the list itself, you'll get a compile error because you're not returning the right type. Here we're returning an array instead of a single item. So let's return the first item in the list because there's actually very little else you can do to make this code compile. And you might notice that you could actually return any index, right? Not just the first item in the list. And this is an example of limitations of type systems. So TypeScript has a pretty advanced type system, but it's not the most advanced. So you cannot actually type check that you're returning the very first item in the list, but you can at least guarantee that you're returning the type that you're expecting. But other languages, if you decide to go and learn more about functional programming, there's a programming language called Idris, which has a more advanced type system and the idea of what is known as a dependent type, which I'm not going to talk about, but if you're interested, come speak to me later. So what I'm trying to say here is that TypeScript is not a silver bullet. So TypeScript or Flow, none of these are really silver bullets, and they're not going to catch every single bug for you. But they're a really pragmatic way for you to strike a balance between productivity and type safety. Now looking at a map function again, if you try it out iteratively, if you return, let's try just returning the items on their own. Again, you'll see compile errors since items is still a list of objects of type A, and it doesn't prove that our proposition is true. If we call the callback function on a single item in the list of items, then we're getting a little bit closer, except we're not returning a list of Bs, only a single B. So logically, the only thing you can do is to take the callback function and run it on every item in the list. And this seems pretty obvious, if you know how array.map works. And what about React? The nice thing is about React that we all love, is its really elegant mental model that your view is a function of state. And stateless components are also functions, right? They take props and they return a React node. So this is a fairly contrived example, but if you try out the number 1, obviously it won't work because learn 1 is a number, not a React node. And if you make it a function that returns a 1, it doesn't compile either. It seems really obvious. So logically, the only thing you can do is to return a JSX element. And if you start thinking this way, thinking about type signatures, what does my function take, what does my function return, and also thinking about pure functions, then it really makes your application, it makes it easier for you to compose functions within your application and for you to do things like creating higher order components, use lenses and things like that. So let's revisit the implications of the Kari-Howard-Lambek correspondence, the idea that proof theory, category theory, and type theory are somehow all linked together, and learn how it can help you write better functions. So here we have a graph of the function f of x is equals to x squared. What I want to call out here is that pure functions in JavaScript are similar, if not the same, as the functions that you learned in high school mathematics. So it wasn't a waste of time. And to refresh your memory on some terminology that you might have learned in high school, Pure functions, as I explained earlier, map an input to an output. So the domain of a function, whenever we talk about a domain, we're really talking about the set of all possible inputs that you could pass into this function. And reversely, the codomain of a function is the set of all possible outputs for that function. So in this case, it's both numbers. Now, has anyone heard of total or partial functions? I'm not talking about partially applied functions because that's a different concept. So I introduced you to the idea that functions can be pure or impure, but that is really independent of whether they are total or partial. A partial function is a function that's not defined for all possible input values. So I want you to think about functions that maybe you've come across or you've written that don't always return values, right? They could return undefined, they could throw exceptions, they could be infinite loops, or even crash your whole computer. So let's take that half function again. And as you can clearly see, this is a pure function, right? It doesn't have any side effects. It always gives you the same output for a given input. But it is a partial function because there are some inputs that you could give to this function that would cause it to throw an error. So let's put it more visually, and let's look at all the possible domains and codomains for this function. So we know from our experiments earlier that if we pass this function any number, it will return you a number. And if you pass this function a string, it could actually return a number or not a number. Thanks, JavaScript. That's actually a feature, not a bug, because JavaScript was designed to work in the worst environments, so it will try its hardest to run your code, even if it's really terrible. But sometimes that's pretty counterintuitive. And you also have your other types, like your voids, which are null or undefined. You have objects, you have arrays, which are really special objects. And these all return not a number, which, by the way, is actually a number. So thank you, JavaScript, again. And if you pass in a symbol, you'll get a type error. So this is not actually an output or a codomain because it's an exception. So now, with a type annotation, if we restrict the domain of this function to only accepting numbers, then therefore the only possible codomain for this function is numbers. And at compile time, this function is total, and it should never be undefined or throw exceptions. But what is a total function? As it seems pretty obvious, but a function that is total is defined for all possible values for its inputs, which means that it always terminates and it always returns a value, never undefined or exceptions. So let's look at another function. Fetch user takes a username and as a string, and then hits some API and returns a promise. And this is a partial function because the fetch could fail. So I'd like to introduce you to something to make this function total. The promise you'll see in the type signature now will resolve with a user wrapped in an either type. So what this means is that now this function can only return a promise that resolves to this type. And whether or not it fails, it's always going to return you the same type. So it's a very, very important concept. So the either type encodes the two possible outcomes. You have left, which represents a failure, or right, which represents success. So what we have here is actually a monad, but I promised you no jargon, so don't worry about what that means. The idea that we're really wanting to take away is that, regardless of what you get back as an output, you want to return something with a similar interface. So you don't have to care if it was a success or a failure. You can handle it in a very similar way. So here's an example implementation or proof of that type signature that I showed you just now. So first, I'm going to fetch a user from my API. And then I'm going to return a left representing failure if the fetch isn't 200 OK. And I'm also going to pass this an error object, which I can use later. So I want you to note that the error here is not thrown. It's just passed into this left function. And if the fetch was successful, it returns you a right, which represents an object that matches that user interface that I said that this type would resolve to. Now when I use this function in my code, note that whether or not the function fails, the return value of this function has a message that you can call safely. So this code on screen won't cause you any issues even if your fetch fails. And when you get into functional programming more, you'll learn more about how to compose these ideas to do more cool things. So you can either like Google category theory or speak to me, or I guess James would be a good person to speak to later. Now the cool thing about the either type is that you can capture the failure and you can do something with it. So maybe I could alert my user and tell them like, hey, the fetch failed. Now let's look at one more example. This function detects the first element in the viewport inside of a scrollable element, a scrollable container. And because this function can return undefined, it's also a partial function. For example, what if I gave it a selector that gave me no elements? So we can reduce the codomain of this function to make this total as well by wrapping the return value in an option type. So now every input to this function will give you an output in this codomain, and it will never be undefined. So the either type and the option type are really quite similar. The main difference is that either will capture the failure value while option does not. And in some other languages, option is also known as the maybe monad. But an option really represents some value or nothing. And so this is the actual function implementation, which is kind of probably hard to read. But you can see here that there are two places where this function can return undefined. If we're using document query selector, it will return undefined if it finds no elements. And array.find as well will return undefined if it doesn't find anything in the array. And if we do find that first visible element, we'll just return that value and let TypeScript know that this is an element. So when you do use this function, you get back the option type, which returns a consistent interface, just like the either type. And both of these objects, some and none, have the map function defined. So in my code, whether or not it found something or it didn't find something, I don't have to do like crazy undefined null checks and like do like a massively nested if statement. Now finally, here's an example of a React component that fetches data. Because stateless functional components are pure functions, you can also make them total. So this component here lets me define 4 possible states in my component. We have no data. We have a scenario where my fetch is still pending, or the fetch has failed, and also the successful case where we have data. So what I want you to take away from this slide is that writing total functions mean that you think about fault tolerance kind of upfront, and you don't think about if my code will fail, but you think about when my code will fail. What do I do? So now I mentioned earlier that domains and codomains describe all the sets of inputs and outputs of these functions that we're writing. So what I'm talking about is that we're talking about set theory. And in set theory, there is the idea of cardinality, which means the number of elements in the set. So I made a very bold claim earlier that the more specific your types and the more constraints you have in your code, the less likely you will have bugs. And again, this is not a silver bullet by any means, but having a lower cardinality in your function means that you constrain the number of possible inputs in the function's domain. So let's start with the basics. A set is informally a collection of objects. And in our context, we really just want to think about the set of all values in the types that we're dealing with. So here I have a type called conferences. And note that this type is not a string which would match every possible string. So because there are only 3 possible values for this type, we say that the cardinality of this type is 3. But if it was just a string, then there could be an infinite amount of strings that would match the type, because any possible string is a string. So what I mean by this is that primitive types are often not precise. So let's look at the cardinality of all the primitive types that we have in JavaScript. So you'll see here that the only types with finite cardinality are booleans, nulls, and undefineds. And you probably don't want to write a program just using those types, I hope. And even the non-primitive type objects have an infinite cardinality, because any possible object that you can think of would match this type. So what I'm trying to say is that defining precise types can really help you reduce bugs in your code. So let's look at a very simple example. We have a generic function here, toString, which calls the toString method on the object that's passed into it. So even though I'm giving this function null and undefined like we did earlier, And we know that null and undefined do not have the toString methods. For some reason, TypeScript will say, this is OK, this type checks. And what this means is that you have lost type safety. This will return a type error if you run this code. So this is known as an unbounded generic function, which means that the type variable t can literally be any type. And you always want to stay away from types like that, like where it can be anything, right? Because it's not precise. And we already know upfront that null and undefined will give me a type error if I call it with this function. So what we want to do is to make this a bounded generic function. So to do this, we add a constraint to our generic type. So non-nullable is not code. It's a type that constrains that generic type t. And it tells TypeScript to exclude null and undefined from t. So now, assuming that everything else has toString defined on it, we have made this function total, since it will always return for every possible input. If you want to think about this visually, imagine a Venn diagram with two sets. So one is a set of nullable types, which are null and undefined. And then one is a set of all types, right? Like here, I only have listed the default JavaScript types, but the types that you've created, that you've defined, would be members of this set too. So what you really want is the difference. You want all of the types minus the nullable types, and that will leave you with the non-nullable types. So the non-nullable type is implemented with conditional types, which is a new feature in TypeScript 2.8. And it's the basis for many of the new helper types that ship with TypeScript. So these are all built into TypeScript, and they're really useful when you're starting to think about constraints, right? Like how you're really starting to think about how your code will be used, and thinking about how you can constrain that code so that it operates on a much smaller range of domains and codomains. So you can check these out in the TypeScript source, which there is a link to at the bottom. We've talked a lot about functions and functional programming concepts, but keep in mind that at the end of the day, you want to be pragmatic. JavaScript is a multi-paradigm language, so you can do both object-oriented or functional programming. But TypeScript is pragmatic. It strikes a balance between productivity and type safety, and you don't have to go all in order to benefit from it. It's not going to solve all of your bugs, but you should be able to catch the obvious ones before your users do. And again, I want you to think about constraints and fault tolerance and make your functions total where it makes sense. I want to close off by briefly talking about GraphQL. If you're not familiar, it's all the rage. It's an alternative to REST and lets you build up a strongly typed schema that describes your entire object graph. So GraphQL has a great user experience. And here we have a visual playground for GraphQL called Graphical, which you can mount on top of any GraphQL API. And you can explore the schema that your GraphQL endpoint exposes. And this lets you know things like type details for each field. So clients of your API just know what to give you, right? And the nice thing about GraphQL and its type schema is that you get a lot of these developer ergonomics that you would in TypeScript. And the only difference now, like TypeScript versus GraphQL, is really that the type system is communicating to you over the network, right? But like to you, when you are playing around with this playground and you're trying to construct a query, you still get the benefits of type safety and even like really nice auto-completion. So being able to drill down into the schema as you develop is a really great developer experience. And because GraphQL has this type system, advanced tools can be built on top of it. It's still evolving, and there's so much more potential in where it could go. So, like for example, just imagine a future where you have a distributed type system with type safety when you, as a UI developer, work with your API or even multiple microservices in the backend. We've discussed a lot today. So first, we looked at an introduction to TypeScript. We looked at generics and how to read type signatures. Generics really help you write reusable types like you do with reusable components and functions. Then we looked to functional programming to see how it can inspire you to write better functions that are both pure and total. And we also explored a high-level introduction to the Kari-Howard-Lambeck correspondence. The idea that propositions are types, programs are proofs of those propositions, and that type checking is really the same as proof checking. And lastly, we looked briefly at GraphQL. and we explored what type systems can give you, even when delivered over the network. And I can't wait to see what else is coming. We've only scratched the surface today, but I hope you learned something about type systems as well as functional, I keep saying that, functional programming, not functionable programming. And by the way, I'm also hiring, so if you want to work on full stack TypeScript, come look for me. But thank you for listening. You've all been great.
All right, thank you, Lauren.